Hi, everybody. So I'm Mael. I'm one of the co-founders and the CTO at Qunnect. My co-founders are Noel Goddard, here pictured, our CEO, and Mehdi Namazi, our CSO, who just became a U.S. citizen today, so it's a great time for a company. So we work on quantum network infrastructure. I'll show you a little bit the hardware we have, what we're working on, and what our partners are currently doing with our hardware. So there's three main pillars everyone here knows about in quantum, right? We have quantum sensing, we have quantum computing, and quantum communications. We think that there's a fourth pillar, or rather a pillar that unites all three of these, which is quantum networking. If you look at quantum computing, for example, you can scale QPUs by interconnecting within a cryostat, by interconnecting data centers, or doing blind quantum computing. All very hard to achieve, but it all requires the technologies of quantum networking. Distributed quantum sensing or using your quantum network as a sensor also is going to require entanglement distribution technologies. And finally, if you want to do quantum communication without trusted nodes, where you want to do complicated topologies, large-scale quantum networks also requires quantum networking in general. Same for time synchronization and other applications like this. So quantum networking really brings end-to-end interconnectivity to harness quantum at scale, and to accelerate the three pillars that are here pictured. So our mission at Qunnect is to bring to market a hardware platform that allows for practical distribution of useful entanglement over distance. Now, what we mean by practical, it has to be field deployable, it has to be scalable both from a physics point of view and from an engineering point of view, and it has to be compatible with existing telecommunications infrastructure. For useful entanglement, it has to be high rate, narrow line with photons, so that you can use these photons for something else than just communication purposes, so interconnecting quantum systems. And then you need to overcome the losses of transmission, topology constraint, which means that eventually we need quantum repeaters. So our solution for this is harnessing the power of atoms for an application-agnostic entanglement distribution platform. We do this with rubidium. Rubidium is ubiquitous in quantum. It's used for sensing, it's used for computing, so it's only natural to also use this for networking. It also works at room temperature, which means that you can do this without cryogenics and without vacuum when you need technology that can scale, that can be miniaturized, but you can also do it in cold temperatures when you actually need the performances, so for example, for end nodes or for computing and so forth. In addition to what I just mentioned, atoms also offer everything that you need for useful entanglement. So this is high spectral brightness, high fidelity qubits, indistinguishable photons, telecom compatibility, interface wavelength compatibility. So this is being able to compatible with the quantum systems that you want to connect between each other in the first place. Also high Heraldian efficiency and the type of entanglement qubits you can do this with either time band or polarization, which are the two dominant ones for doing telecommunications in the first place. So one of our core products is the world's first commercial atomic entanglement source, here pictured on the top left. Currently, we operate with about 80 million pairs per second. That's the max rate we can do. This is with a high spectral brightness and a high fidelity. Because it's based on rubidium, we do spontaneous forward mixing in warm rubidium vapors. We are able to create this entanglement in a bichromatic scheme at the transitions of rubidium. And because it's rubidium, it also means that our photons are highly indistinguishable in the first place as well, which is critical, as we're going to see later down. Our source comes with lasers and everything else that's in there. I'm going to dive a little bit into what this looks like. But the other thing I want to cover is that if you want this to become actually infrastructure, you need to have more than just a device that is a science tool, but also that is robust, equivalent to what we consider classical communications infrastructure to be robust. So this means you need high point-to-point rates. You need to maintain a network-wide high fidelity. You need high network uptimes and durability, automated control layers, APIs, and so forth, devices that are deployable, devices that are scalable, and you need to be compatible with telecom antecedents. It would be absolutely prohibitive to come up with brand new standards or replace everything that's already out there. We have to figure out how we can use the millions of miles of fiber and the facilities already out there and add quantum as a layer to it, rather than building brand new facilities. So our solution to this is our full stack Carina. It's a turnkey solution for multi-node entanglement distribution networks. It has the hardware I showed you before, and it has other hardware that I'm going to quickly skim through. But essentially, it's a telecom compatible, high rate, high fidelity entanglement distribution solution that is in a standard housing footprint that can go into telecom data centers. It's remotely controlled, remotely operated through APIs. It's robust, has a low maintenance. And you can synchronize this over long distance between all the different nodes. In addition, you also have all the other hardware for doing co-propagation and more complicated protocols that go beyond cryptography. So the source that I showed before, this is some data, for example, from a recent deployment of the Carina stack. I think this was Montana. S value of 2.8, a high fidelity above 95, rates above 10 million in that particular deployment. You add to that the lasers that drive the source. You need the lasers in order to pump the rubidium atoms, but one of the really cool things of the atoms is that no matter where in the world they are, they're the same. So our lasers lock to rubidium. It guarantees that our photons are the same also no matter where they are, which means that now when you want to start interacting the photons with each other, we have a high degree of indistinguishability. So really it's ideal for distributed architectures because we don't have to distribute the references through the network as well. We know they're going to be the same regardless of where they are. So these lasers are also meant to be deployable. They can lock for weeks, if not months, controllable with APIs, everything. So again, this infrastructure approach. Next, you need to preserve that fidelity of the entanglement, as I mentioned before. So one of our products is our APC. It's a real-time polarization drift compensation device. It mitigates the environmental perturbations and make this telecom infrastructure quantum friendly, essentially. It's agnostic to your qubit type, relatively agnostic to wavelength, and has negligible downtime and very low insertion loss. So you can really add all this hardware together and start building your network up. This is some example data. Actually, this is taken in Maryland, not too far from here. On the left side is without turning the polarization stabilization on. You can see that basis, the fidelity of the basis drifts very fast. And on the right is the same hardware with the polarization stabilization turned on. And then last but not least, there's a lot of things in the stack, but altogether they allow for co-propagation, real-time monitoring, validation, orchestration, and so forth. One of our devices, our QADI, that's our newest one. It basically gives constant feedback to the user of the quality of the entanglement that they have access to. Basically, it siphons about 1% of the time that entanglement, does full tomography on it, provides the QBER, the S value, the rates, and other metrics so that the user knows if their network is operating and to what degree they can use that entanglement. All this is thanks to the rest of the hardware that's in there, which is taggers, detectors, White Rabbit, and so forth, that is also usable for the user for their own use case, because 99% of the time the entanglement is not used by the entanglement validation, but by the use case that the user wants to do with its entanglement. So about a year ago, we showcased this commercial hardware in New York City. So it's a test bed that we operate ourselves called Gotham Q. It allows our team to understand where our commercial devices are and how we can improve them. On the left is current recent metrics from that loop that's there. It's a total of 432 miles of different fibers, but that actual loop on which we currently run it on is about 34 kilometers, 35. What I want to kind of point out here is that this is a metropolitan area. This is Brooklyn and Manhattan. This is as complicated as it's going to get, and these are not fibers that were dedicated for this. This is whatever was given to us, and we're making it run on that. So really, the ability to maintain this high end-to-end fidelities and these high rates on this infrastructure means that it is an infrastructure equipment. On the top left, you can see when it's compensated versus uncompensated, showing that that infrastructure, if it weren't compensated, is tricky to do quantum on in the first place. And similarly, this is 24/7 operation with a really high degree of uptime, which means that, again, it's not an experiment, it is infrastructure. So that 99.84 is on average what we're getting these days in New York City. That amount of time where it's down is actually for the compensation, for laser lock-in, for anything else that it has to do in the maintenance. And we're trying to get that up to 99.9, and we're going to get there very soon. So, to quote Frank Sinatra, if we can make it in New York, we can make it elsewhere. We went to Deutsche Telekom in Berlin, their T-Labs division, to kind of do a third-party validation. They took our equipment and they reran through Berlin through different paths, adding co-propagation. I think they went up to 100 kilometers, essentially to show that regardless of the path they was taking, regardless of the challenges where the photons were going through, we can maintain those high rates, those high fidelities, and those low downtimes. Once again, showing that this is now almost telecommunications infrastructure. On our side, I'm very excited that we're opening up another test bed. This is an open access user facility that we're opening in New Mexico. This is really to focus with a lot of different partners on the applications beyond cryptography. It's a multi-node network. By the end of the year, it'll be online with 3 nodes. We're going to add more nodes down the road. It's really meant for people to come, to use our hardware, to learn from it, and from us to learn from what users want to do. We have a long list of things we're doing, but if anyone wants to work on this with us, please come and chat with me afterwards. So to circle back to what I initially said, that quantum networking is an enabling technology for the 3 different pillars I think the key takeaway here is that versatile entanglement is a network resource. It's perpetually produced, shared, stored, and can be utilized through these distributed networks. And there's a lot of use cases for this. I would love to hear what people want to do with it. But currently, between what we're doing in-house or what we're doing with customers, the prime ones that we're really actively working that are not cryptography related is eavesdropper and fault detection, ultra-precise time synchronization, quantum position verification, quantum interconnects, and cross-modality conversion. So because the source is bichromatic, you can interconnect, for example, hybrid networks, right, where half of your network is free space, the other half is on fiber, or do frequency conversion thanks to the source and so forth. So it really allows for these different modalities to talk to each other and do interconnects. The more fancy and longer term ones that we're also working with partners on is quantum telepathy, and then some fundamental sciences, because a lot of academic customers are coming to us for our hardware. So I have my personal favorites. I'm just going to go skim very fast through these two. It's eavesdropper detection. So with minor changes to our source, just essentially changing the pump wavelengths, we can operate as a two-mode squeezing source, which allows us to do both tap detection and quantum sensing, distributed quantum sensing. I find this extremely exciting because now we're using this network infrastructure for applications that are in those pillars that was mentioned before. And the other one is quantum position verification. So whether people agree or not with the debate that QKD has an authentication problem, I do think QPV is the solution to it. It not only does it help you prove who you're talking to, but also helps you prove where they are. And it has essentially a layer of anti-spoofing on top of it. It's extremely unique. And thanks to our source having the physical properties for doing successful teleportation transactions, it's a very good source for doing loss-tolerant, loophole-free QPV. So we're actively working on that these days as well. But last but not least, we still have to go towards a quantum repeater. So our team, my science team, is actively pushing all of this. We have a quantum memory, but I wouldn't call this one infrastructure. It's hard to use. It's still really more of a science tool, but it is a commercial quantum memory. It's based, again, on warm rubidium vapors and rubidium, electromagnetic-induced transparency, and we can store qubits for about a few hundred microseconds. We're trying to push this forward. There's a lot of things to do to try to bring this to the same degree of infrastructure that everything I showed before, but we are progressing forward. Recently, we showed that we can store qubits from our source into this memory with a high degree, and then retrieve them with a relatively high fidelity. All again, this is room temperature. And on the other side, the rest of the science team is working on entanglement swapping in a metropolitan area. Again, this is not in the lab, but this is really deployed through New York City, where we are using a commercial product to do entanglement swapping between the qubits. We have preliminary data, but by the end of the year, we'll have a lot of metrics on this and showcase what we're capable of doing with our commercial products to date. But this is thanks to the fact that our source is bright and high fidelity again, that our photons are temporarily broad, and that they are near perfect in distinguishability, which really allows us to get to useful rates of swapping, and then for teleportation and all the other applications that was mentioned before, thanks to this. So the summary here is that if you want entanglement, we'll entangle it. We're really a hardware company. To date, we've sold and shipped over 75 devices. We'll be at 100 by the end of the year. We are supporting currently 5 test beds globally, but we're actively looking for customers who want to adopt our Carina stack, who want to work with us on pilots, on test beds, and who are interested in interconnecting quantum systems, because we can't work on everything and we don't do sensing and computing, so we have to work with everybody else in the room who is. And particularly one last note is I'm extremely excited to see that on the computing front, the roadmaps of computing are openly accepting that quantum networking is most likely in those roadmaps, whether it's near term or long term. And so we see a good opportunity to start working with quantum computing companies to help them doing those interconnects, particularly those that are relatively compatible with rubidium in the first place. That's it.